one, I am going to do a thermal analysis of this two-piece floating rotor and compare it to what happens when you have a non-floating rotor. To set that up, I've put up a couple simulations here, one for non-floating. To simulate this, I'm essentially just establishing the contact area between the hat and the ring, and we're making those items bonded. And then when we're looking at the floating two-piece rotor, I've essentially just established a set of connectors. You can see here that are bolts that go around that connect the ring to the top hat. And what I've done to enable the element of allow it to float a little bit, essentially I didn't add any torque or preload at all to these fasteners, so they're only going to constrain it within the physical constraints of the hole, but not actually provide any preload that a fastener typically would. This would be like a shoulder bolt going through, but not actually providing a compression force on the rotor itself. For all of these examples, we'll be heating the rotor face up to 1000 degrees on both the inner and outer face of the ring. And that really is the quick overview of what we're going to be doing here. For the material types, the top hat is a 6061 aluminum, and I've just done a ductile iron outer ring. I had some other materials in here that I was kind of playing with before I got going, but ultimately I decided to leave them out and just use the fasteners provided within SolidWorks simulations. So let's get started. First, I'm going to show some animations of the floating and the non-floating unit being displaced in the Z direction. It'll look something like this, and the Z direction is basically the direction that the axle would be of the shaft here. We're really only looking at that because that's what's going to impact the amount of pressure the pad is putting onto the rotor itself. I've gone through and looked at the stresses. There's nothing of real concern there, so I'm not even going to get into any of that. We're strictly just going to look at the deformation that is due to the heat. Obviously there's some other loads and stuff that would occur, but we're going to just ignore all of that for the moment and take a look at how heat impacts a two-piece rotor. Alright, let's start looking at some simulations. So here's the non-floating rotor. Let's take a look at the values of the displacement on the surfaces of the rotor itself. So I'm going to select this front face here, and I'm going to select this back face. We're going to hit update. This is going to collect all the points along those two surfaces. What we're really looking at here is our minimum and our maximums. We can see we have a maximum value about 12 thousandths of an inch with a minimum value of about 4.5 thousandths of an inch. Now if we want to go back in, oops, wrong button, and we'll look at some points just across the surface of the rotor rather than the entire surface itself. We can do at location, come over here, and we will just select a few spots along the surface of the rotor just to give us a bit of an idea. A little rearranging here. And again, we can see those values range from about 10.5 thousandths down to about 9.5 thousandths. So we are seeing about a 1 thou delta from the inside to the outside of the rotor with an overall displacement of around 10 or 11 thousandths of an inch. Now if we take a look at the floating rotor and we do the same sort of quick analysis, we'll select the front side of the rotor and the back side, and we'll see what kind of values we have. Alright, so our maximum's around 9.5 thousandths with a minimum of around 2.5 thousandths. So a little bit less overall. And if we, again here, I'll have to, look at some point values along the front surface here. Do a little rearranging. Oops. Just made a mess of it again. So if we look at these values, we can see we have about 8 thou right here and a minimum of 7.4. So this one's a little bit more consistent. We definitely have less than a thou, maybe half a thou of discrepancy and deviation across the front face of the rotor. So that will definitely show itself in how much pressure is being put on the pad when these get real hot. Obviously the non-floating will present a little bit more pressure on this outer side, and then it'll decrease as it goes inward, and the floating rotor will be a little bit more consistent, applying a similar pressure across the entire face. Well, I think that about does it for this video. Stay tuned for the next one. I'm going to keep on this brake theme and look at doing some CFD analysis on the rotor. You can see this guy here has actually some curved vanes in it. We'll look at how those work versus a non-curved vane, and hopefully that'll be an interesting thing we can take a look at. So until next time, see ya.